Dan McInerney from Protect AI, and today we're looking at API attacks against ChatGPT. APIs aren't like websites where you can just click every link to populate burp. They usually come with some form of documentation, like the Open API specification file, which lists out all the API calls and variables. Your first step to testing APIs is to acquire the specification file and load it in one of two ways. First, you can try the Burp Suite extension Open API Parser, which is available from the B App Store, but I run into parsing errors with that extension fairly often, so I usually end up just using Postman. Postman is an API testing tool that works really well for parsing even bad specification files. Inside of Postman, we are going to import our collection file, which is our Open API specification file from OpenAI. Then we're going to change the authorization to bearer token. The token's a variable here, and so we're going to change that variable over in the Variables tab. Now, once we've done that, we have this nice big list of all the API calls you can make. So we are going to hook this up to Burp through Settings, Proxy, Add Custom Proxy, and put in our Burp port and IP address. Now that we've set up Postman with all the API calls in OpenAI's API specification, we just click Run, and it'll send all these API calls over to Burp. It'll get sent to the Proxy tab, and we'll just right-click on each one of those and send them all to the Repeater tab. So right here you see all of the different API calls: create completion, retrieve model. We're looking at create edit right here. So we're just trying to fix this input, and we're asking the AI to do that. Now, what I've noticed in my experience is that mature organizations like OpenAI are not going to send out an API that has common vulnerabilities in it. So you're not going to see things like simple SQL injection usually. So we'll need to perform advanced attacks like complex attacks against their OAuth authorization flows, race conditions using Turbo Intruder, or HTTP request smuggling. HTTP request smuggling is what we're going to be focused on here. Simply put, modern websites aren't run on a single server. There's a front end that handles the user's request and forwards it to a back-end server. If there's a mismatch in how the front-end server parses the length of the request versus how the back-end parses the length of the request, we run into severe issues. So we're going to be sending this request to the extension HTTP request smuggler and launch all scans. Extensions, request smuggler, launch all scans. Now, while that goes on, we head over to the Logger tab. The Logger tab tells us all the different requests that are being sent by the extension. Now, the most important part of this is the length. That is the response length. And you'll notice there's a little bit of an outlier here. This one is 1148 bytes long, but everything else is 592, 832. So let's click on this and see what it is. It looks like a regular request smuggling attempt where we terminate the request with the double new lines, and then we send some extra data and see what happens. And the response is curious. We sent a single request and got 2 responses. So this tells me that something weird is going on. Burp actually didn't report this as a vulnerability or anything interesting, which is why we always look at the logger to see what's happening. Now is the point where we take this, we send it over to Repeater, and we start chipping away at it to figure out the minimum possible information necessary in this request to trigger this strange double response. Here is the original request that we pulled out of the logger. Now I'm going to skip over the tedious part of stripping this down to its bare essentials to trigger this double response and just go right to it. So here is the minimum example. We have an accurate request right here with an accurate content length, followed by a second accurate request with an accurate content length. And we're greeted with 2 responses and 1 response, both 200 OK, both valid responses. Now something to note is that there's no double content length header, and there's no transfer encoding header. That means this is not a cl.cl request smuggling attempt, and it's not a te.cl request smuggling attempt. It's actually an HTTP request splitting attack, which isn't a vulnerability in and of itself, but it can be used to exploit quirks in the architecture to get turned into an exploit. One way to do that is by stuffing 20 of these requests into a single request and then sending a whole bunch of those. So right here, we have 20 requests inside of 1 request, and we do that 11 times. Make sure that you have content length unchecked and make sure this is HTTP 1.1. Then we're going to send group in separate connections and see what happens. The responses come back and we see there's 6 200 OKs here 11 here, 7 there, 1, 1, 1, 1, 1, 1, 1, and 1. Now the final date and time of this was 1852-24, and we started at 1851-42. We got, I think, 24 responses in less than a minute. Now, Text DaVinci Edit 01, the model we're using, has a rate limit of 20 per minute. So we just bypassed that rate limit. Well, we tested a bunch of other ways of doing this, of exploiting this request splitting attack, trying to change the authorization headers, putting different authorization headers in here. But you can use a little bit of creativity and find some other exploits, we believe. We do not believe this is the end of the ability to use this for other attacks. Denial of service might be possible. Most impactful, it might be possible to influence the back-end ordering of the responses so that we get other users' responses when we send these. There's a lot of different creative ways that you can abuse this quirk. And we look forward to seeing further research in this area of advanced API attacks.
Ready to spotlight your skills? Join the hunt on hunter.com.